So, we have learned with you that after the long discussion about what is the nature of light, is light a wave or light is a beam of particles, after the Young's double-slit experiment, there was like pretty much no doubt. Light is a wave. Light is a wave. And everyone would say, okay, Newton might be wrong, even greatest people sometimes can be wrong. But then some physicists discovered something called photoelectric effect. When the surface of the metal is illuminated with the light, the electrons coming out of the metal. And investigating this effect, they were found some facts which did not fit into the wave. So let's have a look what is that experiment, what was done, and how it could be explained. And by the way, this is an example of one of the best done experiments, because carefully choosing what are independent variables, what are the dependent variables, what can affect and what can be affected, lead to those results. So here is this experiment. We have metal plate. It's all in the glass tube from where air was pumped out, so it was pretty much vacuum inside, to prevent electrons coming out to collide with the molecules in the air and stop. We have source of light, which we can change wavelengths or frequency, and we can change intensity, so we can change brightness of the light. And we also, electrons will then come out of here, they come to another plate, so we can measure current that will flow through this. And we can apply voltage between those two plates. So what will be the independent variables that we can change? Light, wavelengths or frequency of light, the intensity of light, how bright light is, and we can change the stopping voltage. What stopping voltage, what I mean stopping, we can change voltage if we apply minus here and plus here. Will it stop electrons from getting through? We apply minus here, plus here, electrons coming from this metal plate. What charge electrons have? Negative. We have negative, positive, negative electrons will be attracted, so they all will come through. Everything that will comes out as a result of the light absorption will get through. But if we apply voltage in the opposite way, minus here, plus here, we'll have electric field that will push electrons back. But the electrons coming with some speed out of the metal, they're coming with some kinetic energy. So when we apply enough voltage to stop all electrons to come in, they call stopping voltage. What information the stopping voltage will give us? What it tells about the electrons?
Speed.
Their speed, their kinetic energy, their maximum kinetic energy. So let's see what happens. Let's say we start from wavelengths, from red light. And I will make very, very bright light, maximum intensity. and we're not applying any voltage, zero voltage at the moment. What from the wave point of view, the intensity is? It's the energy, how much energy light has. It's the amplitude of the wave. The more intense light, more bigger amplitude of the electromagnetic wave, so more energy. But when we have red line, doesn't matter how bright light we put on the metal plate, no electrons coming out. And then let's start let's increase frequency. So making wavelength shorter and increasing frequency. And suddenly, at certain frequency, we get electrons coming out. How wave theory can explain it? Why at some frequencies electrons not getting out, and as soon as we get to certain frequency, called threshold frequency, the minimum frequency at which electrons get in, they get out. And then if we make frequency even more, you see what happens, the electrons not just coming, they come in, you see, faster from there. That's one thing. And I will even make intensity very low. I will make intensity very low. According to the wave model, very low intensity, there will be no electrons coming out because not enough energy. Or electrons will come out, but with a time delay later on. Because there will be a wave coming, electrons absorbing the energy coming with the wave, get more energy, and eventually get out of the metal. But it's not happening. Electrons were either getting out immediately, if the frequency was above threshold, or not coming at all. Now I will apply the stopping voltage. So I will apply the negative voltage. So as you can see now, at certain voltage, electrons cannot get through electric field. They're getting out, but electric field pushing them back. And again, so when we stop even the fastest electrons, the voltage gives us, the stopping voltage will give us how big the kinetic energy is. According to wave model, if you make light brighter, more intense, we need to change stopping voltage. Because the electrons will have more energy, but no, not happening. But if I will now increase frequency even more, without changing stopping voltage, I increase frequency of the light more. And now we get some electrons coming through. So clearly kinetic energy of electrons related to the frequency of the light. So those findings from the photoelectric effect, from this experiment, they clearly show that the wave property of wave theory of light cannot explain. It cannot explain the fact that there is a threshold frequency. That the first thing, according to the wave model of light, energy of the light related to its brightness, not to frequency. Second thing, we found that so now to stop electrons, I will need to make voltage even more negative. And now I again can stop all electrons. If I will make frequency even higher, then I will need to apply more stopping voltage. Again, wave theory cannot explain it. According to wave theory, the stopping voltage should depend on the brightness, but not on the frequency. And again, according to the wave model, if light is dim, not bright enough, electron might accumulate this energy over the time and get out. So all those things puzzled physicists. The wave model couldn't explain it. And then Einstein comes up with the explanation. By the way, Einstein received his Nobel Prize for physics, not for the relativity, but for explanation of the photoelectric effect. Effectively, we can say that the photoelectric explanation of the photoelectric effect laid foundation of the modern physics. It was a beginning of the quantum physics. So, what was Einstein's idea? By the way, the first part was not his idea. There was idea developed before him, ideas of Max Planck, who, if you can recall from the last year, or Unit 1, some not last year, from Unit 1, when we were learning the black body radiation. If you can recall the graph, when we have that is the wavelength, and that's intensity, and we have curve like this, and if we increase temperature, so any object was emitting, not the best drawing, I think it's more like this, but the idea is any object that has temperature emit electromagnetic wave. And the maximum, at what wavelength is the maximum of the radiation? Who can recall which law relates these wavelengths and the temperature? Who can recall from Unit 1? Yes?
By Higgs? No.
Wend's law.
Oh, yeah.
Wend's law, that wavelengths at which the maximum radiation times temperature in Kelvin equal constant. And if we increase temperature, wave maximum will be at the shorter wavelengths. But the thing is, that was well known from the experiment, this. But the theory which explained how the body created electromagnetic radiation, according to the existing model, if we were decreasing wavelength, this graph should look like this, going to infinity intensity, which was called I think ultraviolet disaster or something like that, because it wasn't going to infinity. And to solve this problem, Planck, he developed an idea that light not emitted continuously, emitted in the small portions, which we call now quantums or photons, and the energy of each such portion is equal constant times frequency, where h, no wonder it's called Planck's constant, and we will be using it now a lot. There are two values for it we will be using. One is for in joules, so 6.63 times 10 negative 34 joules second, or 4.14 times 10 in the negative 15 electron volt seconds. So when Planck made this idea and did calculations, he perfectly received this curve. So that was Planck's idea, that the light is emitted in portion. And the energy of each portion equal Planck's constant times frequency of the light. And when Einstein looked into the photoelectric effect, and knowing the Planck's idea, he said, stop, light is a beam of particles. And each particle, photon, each individual particle, photon, has that much energy. Each photon brings that much energy. And one electron can absorb only one photon. And there is minimum amount of energy for electron required to get out of the metal. and that called work function. I think now in the latest textbook they're using, instead of W, they're using, I think, this symbol, very similar to flux. For work function, I will be using still. It was always W, work function. What is work function? It is the minimum amount of energy needed to get electron out of metal. Work function is a minimum amount of energy to get electron out of metal. Why? First, it depends on the metal. Let's say copper will have one number, lithium will have another metal. Each metal has its own value. Why it's important to say, if you did not say the word minimum, you will lose the sense. Why we say minimum? In the metal, as you know, electrons from the outer shells are free. Electrons from the outer shells of metal are free. But some electrons are next to the surface. And that amount which are like they already at the surface, and the amount of energy needed to get this electron out is a work function. Because there are some electrons, they are a little bit further down. And there will be more energy needed to get this electron out. So important that the work function is the minimum energy to get electrons which are like ready to get out, but still need some bit more push, some more energy. That's called work function. So, and what Einstein said, that when we have photon brings that much energy, it's energy of the photon. And then it is just a law of the conservation of energy. What this energy is used for? Some of it used to overcome work function to get electron out. And what's left will be kinetic energy. So this is, effectively it is law of the conservation of energy for photo effect.
Right,
this is a
HF first.
HF is the H is the Planck's constant, F is the frequency of the light. And what Einstein said, this is the equation describing photoelectric effect. This is the energy, how much energy one photon brings. And that energy, when electron absorbs that photon, what happens with that energy? Some of it used to overcome work function, just to get out. What's left is kinetic energy. So if we have kinetic energy 0, we just get electron out. Doesn't have anything, but just get out. We will have that HF equal work function, and that will be threshold frequency. The minimum frequency required for electron just to get out. That energy of the photon just enough to overcome work function, just to get out. 0 speed, but get out. And from here we can see, if frequency will be less than threshold, energy of the photon will not be enough even to get electron out. But if frequency greater than the threshold frequency, minimum frequency, what will happen? Electron have kinetic energy and flux. Okay, we'll continue to talk about the photoelectric effect next lesson. Like, subscribe and donate to help fight terrorist countries and organizations like Russia and Hamas. Support Ukraine and Israel.